In section 14.5, we apply what we've learned about acid-base equilibria to what are known as polyprotic acids. So far, every acid that we've looked at has been what is described as a monoprotic acid, and these are acids that only have a single ionizable hydrogen atom. So these might be weak monoprotic acids, like acetic acid, or it could be a strong monoprotic acid, like hydrochloric acid. The key feature is that they only lose one hydrogen ion when they ionize. So even if the molecule, like acetic acid, has multiple hydrogen atoms in it, there's only one that is actually lost. So something to keep in mind is that if a molecule does have multiple protons, the ones that are most likely to be ionizable are those that are attached to highly electronegative elements, most commonly oxygen or a halogen. Polyprotic acids are a little bit different. Polyprotic acids have more than one ionizable hydrogen atom. And again, they can be strong, like H2SO4, or they can be weak, like H3PO4. And we can tell if they're strong or weak, remember, by comparing the number of oxygens to the number of hydrogens, and we need at least 2 more oxygens than hydrogens in order for it to be classified as strong. So we might think of, an acid which has 2 ionizable protons is referred to as being diprotic, and an acid that has 3 ionizable protons is referred to as being triprotic. So we can see here that in the case of the strong acid, that the first ionization is complete. It's not an equilibrium at all. So 100% of our starting material loses a single proton. But then for our second ionization, once we generate a charged species, it's behaving as a weak acid and there's an equilibrium. For our weak triprotic acid, H3PO4, what we see is even the first ionization is incomplete, and it's an equilibrium right from the very beginning. What we observe for all polyprotic acids is that successive ionization steps are always less complete than the preceding step. What I mean by that is that the first Ka is always bigger than the second Ka, which is always bigger than the third Ka, and so on. And the reason is, when we lose the first proton, we're losing it from an electrically neutral species, but when it comes to losing the second proton, we're losing it from a negatively charged species, so that's going to be harder for us to lose a positive thing. And as we move on and we ionize more and more and more, that negative charge builds up and it becomes more and more difficult to separate off the positive proton. So that's a kind of consistent observation that Ka2 will always be less than Ka1, and Ka3 will always be less than Ka2. Most of the time, in fact, we're going to assume all of the time in the problem that we encounter, you only need to consider one of the steps, one of the ionizations, in order to determine the pH of a polyprotic acid. And I'll explain why. If your acid is a strong acid, then we can assume that the first ionization step is complete. So what that means is we're just going to start at the second ionization, and our initial hydrogen ion concentration will be known to us. So we only have to do one step. For a polyprotic weak acid, we're going to kind of take the reverse process, the reverse sort of a procedure. And what we're going to assume is that every ionization beyond the first one is so insignificant, that the Kas are so small that we can just ignore them and just determine the pH on the basis of the first step. So I'm going to illustrate both of these assumptions now and hopefully show that they are correct. So we're going to begin by looking at a diprotic strong acid, and we're going to use H2SO4. So this question asks, the first ionization of H2SO4 is complete. The ionization of HSO4- is characterized by Ka2 equals 1.2 by 10 to the minus 2, what is the pH of a 0.2 mole per liter H2SO4 solution? So what we can assume is that our 0.2 molar H2SO4 dissociates completely to form a solution of 0.2 molar H plus and 0.2 molar HSO4 minus. And what we're going to do is we're going to pick it up by doing an ice table for the HSO4 minus anion and figure out how much acid is produced in this second ionization and then add it to the 0.2 moles per liter of acid that is produced in the first step. So this is how it's going to begin. We're going to begin with an ice table for the HSO4 minus anion, and that's going to dissociate to form H plus and SO4 2 minus. We have the Ka for that. It's 1.2 by 10 to the minus 2. So my starting concentration of HSO4 minus is 0.2, and my starting concentration of H plus is 0.2, and my starting concentration of SO4 2 minus is 0. So what's going to happen now is it's going to move towards the 0 because that's the only way that it can go, and some of my HSO4 minus will be consumed. I'll make some extra H plus, and I'll make some SO4 2 minus. It's 1 to 1 to 1, so everything there is 1x. So now I'm left with this situation where I'm going to have 0.2 minus x moles per liter HSO4, 0.2 plus x H plus, and x SO4 2 minus. So the first thing I'm going to do is I recognize that that is a fairly small K. It's not that small. I'm going to check to see if I can use the approximation that the equilibrium amount of HSO4 minus can be approximated as 0.2. So I take my initial concentration of HSO4 minus, divide by the Ka, and see if it's bigger than 500, and it's no good, and I'm sad because now I have to use the quadratic formula. So this is where we're at. Ka is equal to the concentration of my products divided by the concentration of my reactants. And then I've just got to kind of solve for x. So I distribute that top line there, and then I kind of keep reorganizing things, collecting like terms and so on, until I have the form of a quadratic equation. And there it is there. I've just left Ka as it is rather than writing out 1.2 by 10 to the minus 2 every time. So what have I got here? I got A is minus 1, B is minus 2 minus Ka, which evaluates out to minus 0.212. And then C is 0.2 lots of Ka, which evaluates out to 2.4 by 10 to the minus 3. So I use the quadratic formula, and I solve for, and I find that there are two roots. And only one of them is realistic because we can't have a negative concentration. Such a thing doesn't exist. So X, which represents the H plus made in the second ionization, is quite small, right? It is 0.011. So how much have I made? How much H plus have I made? Well, I made 0.2 in the first one, and then I made X in the second one. So the total H plus concentration is just going to be those things added together, right? So H plus is just 0.2 plus 0.011, gives me 0.211, and then I want the pH because that's what the question was asking for. What is the pH? So I have to take the negative log of that number, and it's 0.68. So the key here was I didn't need to do two ice tables. I just assumed that the first ionization was complete, which was nice because it told me that in the problem, and then I just did a single calculation, and the focus was on figuring out how much H plus was produced in the second ionization. It's not too bad. Polyprotic acids, when they're strong, it's fairly easy to figure out the pH. It's not a lot different from what we'd been doing previously. So now we need to do an example of when we have a solution of a weak polyprotic acid. So we're going to go with the example of H3PO4. And it says the ionization of H3PO4 is described by Ka1 equals 7.11 by 10 to the minus 3, Ka2 equals 6.32 by 10 to the minus 8. Okay, yeah, and Ka3 is 4.5 by 10 to the minus 13. So you can see they get a lot smaller as we go through there. Then it says, what is the pH of a 0.2 mole per liter H3PO4 solution? So all we have to do is an ice table for this guy, and then we're going to assume that the amount of H plus made in the next two steps is so small that it can be neglected. So let's see how this works. So I've got H3PO4 in equilibrium with H plus and H2PO4, and I had 0.2 mole per liter of this guy to start with, and I have none of that, and now it comes into equilibrium. So it's always going to move towards the zeros. So this will go down by X, this will go up by X, this will go up by X, leaving me with 0.2 minus X of my starting acid, and then X moles per liter each of my H plus and my H2PO4 minus. So again, I want to check whether I can approximate my 0.2 minus X by just 0.2, because that's going to make the math really easy. So I take my starting concentration of my acid, divide by my Ka, and see if it's bigger than 500. And again, didn't work, unhappy. I'm going to have to do some more difficult math. So let's go through and try and solve. So it is products over reactant concentrations. So that's just going to be X squared on 0.2 minus X. And then I've got to sort of reorganize this into the form of a quadratic expression, which I've got there. So A is a minus 1. B is minus Ka, and then C is my initial concentration 0.2 times by the Ka, which I've evaluated there. So when I solve this, I get two roots. Again, one of them is negative and one of them is a realistic positive number. So it's got to be that guy for X. So this represents the amount of acid that was made in that first ionization. Now remember, we said we can ignore the acid that's made in the next two steps because it's going to be a really tiny amount. So we can just go ahead and take the negative log of that number and get the pH. And it's acidic, right? 1.47. So yeah, that looks very good. It's always good, if you're figuring out the pH of an acid, it needs to be less than 7. Keep that in mind. If you get like 10, you made a typo somewhere. Okay, so the question is, was it really appropriate to ignore the other two? So let's kind of do it again. Let's pick up. So I've updated my, let's look at the second ionization. So we're going to begin with H2PO4, and it's going to make H plus and HPO4 2 minus. And so this was 0.2 minus X, which turned out to be 0.166. And this was X was my starting amount. And then I have none of this, and then it comes into equilibrium by moving towards my zeros. So this is going to go down by X, this is going to go up by X, this is going to go up by X, and this represents the acid that's made in the second ionization. So I'm not going to do quadratic formula, I'm going to get smart and I'm going to use the solver. So I've just got to keep my Ka straight. So my second Ka is 6.32 by 10 to the minus 8, and that's equal to my product concentrations divided by my reactant concentrations. And I use the solver, and you can see it's a really small amount. So I take my amount of acid that's made after my first step, add what was made in the second step, and this isn't written out to the correct number of sig figs here, and it's hardly any, right? This is the stuff that was added in the second step. And when I take the pH of it, and I didn't round off at all, I got exactly the same number to 3 sig figs that I got the first time when I neglected this. So I could definitely neglect that. And if we go on and we do the third one, then you see that it's just starting to get ridiculous, right? So our concentration of HPO4 2 minus is just going to be X, which there it is there. Our concentration of H plus is pretty darn close to 0.034. I did actually put the whole thing in when I did the math. And the concentration of PO43 minus is 0. So it's going to move towards the zeros, because it always does that. It has to, can't move away from the zeros. So that's going to go down by X, that'll go up by X, that'll go up by X. And working through the math again, I'm going to solve for that. This represents how much was made in the third ionization. So I'm using Ka3 here. Ka3 is equal to 4.5 by 10 to the minus 13. to make sure I pick the right one. And then again, it's products over reactants. And when I used solver, you can see it's an infinitesimal amount of hydrogen ions that are produced in that third ionization, 10 to the minus 18 moles per liter. That's undetectable amounts of hydrogen ion. Anyway, I did the math just to prove the point. So 0.034 plus that number, guess what? To any reasonable number of sig figs, it equals 0.034. And then the negative log of that, I got exactly the same answer. So I really didn't need to consider the second or the third ionization in this problem. It produced the same answer as only considering the one.